Live. Uh, Tyler, ask me your question again, please. Right.
So is that important besides the fact that they have different densities and that they cause different types of weather? Flying through the different air masses.
The big three are understanding where your weather comes from and how it changes seasonally. Understand that weather, just weather, there's four types of flying: VFR flying, IFR flying, weather flying, and mountain flying. The weather course that we will ultimately deliver is going to be a semester-long aviation weather course that, God willing, will give science credit to kids as well. The reason being is because it is so complex with what's happening. To give you an idea, the snow that we are going to get late tonight and through Wednesday night, the things that are happening to make all of that happening with the jet stream, with our water vapor level, with the air coming in from Canada, which is normally dry air that's coming in from the north, but it's ultimately meeting air aloft that has much more water vapor in it, that's going to be creating kind of this convective action going north, cooling off that warmer, moisture air, giving us this snow, giving us a northwest thing. All of these things happening. You know, a butterfly flaps its wing in Peking, you know, it rains in Paris or whatever the deal is. My point is this. All of those things, the three different zones that you have, north and south of the equator, all of those three basically operate in a loop. And if you think of it from the equator this way, so the equator, that air is going to rise, right? From that point, wherever that is in that tropical divergence zone, will begin its kind of loop toward the north. As it gets to a certain point, it cools. When it cools, it descends. Well, as that descends, you have another loop in the mid-latitudes that goes the opposite direction. Then that creates another one in the northern loop that creates even more pressure. Those things expand and contract. With seasons, they move with the jet stream. And so all of those blobs, if you think about that lava lamp example of weather, you know, like that, that's kind of what that is. The big thing about those three zones is understanding what the basic circulation patterns of those three zones are. Understanding that they expand and contract. They actually also, you know, in the summer months, you know, when our Earth is in a little different place, they also expand vertically with things. Correct. And they move. You know why? It's just like if you, you know, have, like, if your parents are like, you know, have an old turntable at home, and you think, okay, you want to know what the Coriolis effect really is, kind of like, or a Lazy Susan like this. It's better if you have, or a potter's wheel, and you have something spinning, and you take your finger and you start at the center and you draw a straight line to the edge while it's spinning, and you kind of see what happens with that. That's kind of an example of the Coriolis effect that we have with our weather. But that's not the only thing. It's pressure dependent. Because again, you can have the actual opposite. It varies that you have a system that backs up from the east to the west because of that, but it is going north or south. That's a realistic thing that can happen because of the pressure differences. You know, if you have a lower pressure to the south, it's going to dive off to the south. If you have that lower pressure to the north, it's going to dive off to the north. So it's like, you know, how do you know? The point here is this. As we'll talk about as we wrap up this section on weather theory, which leads into the next section, which talks about the weather reporting piece. There is no one thing you can look at with regard to weather. You have to look at all the tea leaves to kind of see how all of that stuff works. I know that's a very circuitous way to answer your question there. But that's kind of the way that those blobs work. Understanding that those three zones exist, what they normally do, and what you might expect long range wise from that, especially if you're planning international flying. That's like huge. Even beyond that, hemispheric, going from the northern hemisphere to the southern hemisphere, because the worst weather on the planet is in that tropical zone. It's in that, because that's just, yeah. And it, does it go north? Does it go south? Does it go north? Does it go south? And again, it depends on that pressure, which way it goes. And so there's always freaky weather happening there. The point is that the more you know about that, the better off you're going to be. From a commercial pilot standpoint, especially going long distances, that's really where you want to have your weather chops, and to really kind of understand what can you really expect. You'll see the forecasts, but over time you'll get that little voice in the back of your head that experience tells you to say, ding, 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 I've seen this before. Anyway, Kylie. More than you bargained for on that?
No, it was good.
Go.
So if it's, do you treat rain the same as snow, or do they have different situations?
Ask me that again.
When you go up to higher elevation, is the rain, couldn't they both cause icing? So would you treat them the same, or would you use different,
Give me an example.
say it's snowing out,
Okay.
but very lightly.
Okay.
Would you fly or not?
Depends.
Depends if it's like a lateral moving cloud, like cumulonimbus clouds.
How isolated is that snow? How cold is it? Because if it's below that freezing band of minus 15 C, and we know that now everything is frozen, and we know that nothing is going to stick to that airplane, that's when it starts, So if it's much colder than that, let's say it's minus 20 Celsius, and there's just an isolated pocket of just this light snow, and everything else is frozen, yeah, you could probably fly. But the big boys are going to get de-iced. That's just part of their protocols, especially coming in and out of Aspen or any mountain airport. They're going to pay for the de-ice on that. It's one of the reasons that your tickets cost so much here. Again, because you got to pay for that. Little fellas, like me, with those kinds of things, it would have to be awfully cold for me to say, okay, I'm just going to get through this light pocket. But then I would only launch if I knew that I had a bailout point somewhere else that I could go to, number one, get out of whatever it is that's causing this, and two, if there's the possibility of finding warmer air somewhere, that's realistic, then yeah, I'd go. If not, we're going to sit there, we're going to have a cup of coffee, we're going to let it pass, we'll launch in an hour. So, I mean, that's kind of it. The big thing is that if you get this rain or this mist, which is like the worst, let's say it's 38 degrees on the ground and it's mist. Okay? Well, let's put it this way. Let's say it is 3 degrees Celsius. 3 degrees Celsius, and there's mist. Would you launch?
Probably not.
Why?
Because once you got higher up, then the temperature would go down,
Mm-hmm.
and then it would start to ice, because especially since it's mist, it would just go around your airplane and just ice up everywhere.
Bingo. Your lapse rate, you lose on a standard lapse rate, how many degrees Celsius per 1,000 feet? Maybe 2. Okay, so when you look at this and you think, okay, what is it that I need to get up to? Well, if you're looking at this and you're thinking, okay, 3 degrees Celsius, well, here we go. I'm not even at pattern altitude before I'm in icing conditions. And so that's kind of what we have to look at. It's not just what's happening here, but we have to think, okay, because I know what's happening here, and that's it. That's where you look at your temperatures and winds aloft on this, which we'll go into here with this in these things. So
Would the situation be different if you were in a commercial aircraft that was bigger, or would you still not go because of ice?
in the situation that I just described right there, even the big boys would have to second guess that one. And the reason being is because you can get the de-ice spray, that glycol stuff that they spray over here. And by the way, Aspen has a very, very unique reclamation process where all of that stuff that gets sprayed on the tarmac actually gets recycled in there, which is really kind of a cool thing. You know, you kind of think, okay, I spray all this stuff on here, where does it go? It gets recycled. It gets collected in these drains around that side of the run-up area over there. It gets collected and recycled to be ultimately reused. So it's kind of a cool thing. But they spray this this glycol solution on these aircraft. But that's not necessarily a fail-safe, because you can get into a situation like that, especially when you have this mist, and then all of a sudden you get into that freezing mist. Well, that's clear ice. And so, you know, then in that case, it's just like the worst ice, you know, ever. And even the big boys would have to really think about that one. So.
Well, you're gonna hate this, but it's time to go. Alrighty.
Holy crap. Okay. Well, guys, again, this is the second day that I've messed you up. Taco Tuesday, I start talking at noon. And we're going to start going, we're going to pick this up. Honest to God, we're going to start on wind shear. Okay? And we're going to make this happen. Yes. Yeah, I will. You can send me texts. Hey, Mr. R, you look fabulous. Okay. Guys, well, guys, don't thank me. I feel bad that I didn't get this going. So, okay. All right, guys. See you guys at noon. Okay, my pleasure. And I think we should be live. Now, one of the things that has kind of happened a little bit was when we adjust the privacy settings of the content of this, it alters the way that you get access. I'm trying to get it figured out because ultimately what will happen is that there will be a controlled password gateway to this programming. That's where your email address comes into play. The reason you haven't gotten one back from me is because we haven't figured out how to control the privacy settings, still allowing you to actually see what's going on here on our YouTube channel. As soon as we do that, then I'll verify your emails as well and then send those to you. It'll be an active type of a thing where there will be some work required on your part, basically answering some questions and going on and subscribing and all this other stuff. So that'll be one of the things that you guys are going to have to do. Just you know, letting you know. Hang on here. Let me do this. Let me shut this off. I thought that was on. It is on. I don't know. That may have been my phone. Yes, it was. I thought it was my watch. Okay. So just know that that's coming. We rewired from an electrical standpoint all of the stuff upstairs in the studio thing in the house before Christmas, and then we had people in, and I just didn't get anything done that I thought I was going to get done. But I will be here for about 3 weeks getting some stuff done here also. Another thing, just to kind of let you guys know, the Aero build program on the airplane that we have in the bus barn. Kids in 8th grade will have the opportunity to work with us to build this airplane. We're going to be scheduling a series of meetings starting next week. And as we do that, we'll be talking about how that's going to work schedule-wise, kind of what our timeline looks like it might be, etc. So just keep that on your radar as well. Solomon.
About the Aero build, my mom has been trying to get information about it for some time now, and she hasn't gotten a very clear picture of it. She's read this giant project that's supposed to be appropriate for the thing that you have to bring in, like, to approve yourself and everything. I don't really know what she told me either, because she barely knew what was going on. So my mom asked me to ask you about what exactly is Aero build about.
There'll be two things. One, well, thank you. One will be the build of the Velocity that we have in our bus barn. The other is going to be a class building small UAVs here, and that'll be Thursdays after school. That's going to start after second semester. I believe our first class of that, it's going to be after school, so it'll go from 3:30 to 5 on Thursdays. And it is, I think it's the first Thursday in February when it actually starts. So, because our semester doesn't end until like right before the last week of January. And then we have that first week of January just to get classes started on the second, that semester thing, and then we start the extracurricular stuff after that. Similar. Yeah. Yeah. So, yeah. And there's going to be more stuff that'll be coming out about that. Mrs. Benton was working on some stuff. She's not feeling well here this week, so she's kind of under the weather. But that's going to be that'll be kind of one of the things that'll be coming up here as well. In addition to that, discovery flights that we have here for our airplanes, for you guys to actually get up and really do a little flying. It's basically your first lesson to go up and fly. Those of you that want to do that, then we'll be talking about how we make that happen, for that first discovery flight thing, and get you guys going that way. We have updates that we're going to be doing here not today, starting tomorrow on the desktop sims. We will begin our desktop sim work next week. I'm actually going to Austin, Texas on Thursday, and I'll be with the folks at Redbird all day on Friday, and there will be several things that we're going to be doing there just to kind of make the simulator stuff here a little bit different than it's been in the past, a little bit more robust, and a little bit more accessible, and different things that you guys will be able to do. We have to kind of do that because we have a group of guys here that has done a lot, even instrument flying, and then we have a group that never touched it. So, we have to have things that work for everybody. So there will be things that we'll be doing there as well. Just to resist the temptation, Joseph, let's go ahead and just put that back where it was. Yeah. So that's a little bit of an update. We're going to go ahead and start up again here on instruments. If you turn in your hymnals here to chapter 8, page 12. First of all, tell me again what 3 categories of instrumentation there are. Take a look at your notes. The 3 major categories of instruments. Gyroscopic is one. Good. What do we call that? They are pressure instruments, but there's another name for it. That's the last half. That's the last half. There's another word that comes in front of that. Pitot-static. Thank you very much. Pitot-static. Pitot-static instruments. Gyroscopic. And lastly, but not leastly, what? Solomon. Magnetic. Well done, lad.
Chapter links are, it says print on it.
I don't know. Again, this is why I suggest not having your notes or anything like that on these computers, is because they're fallible. So, pitot-static, gyroscopic, and magnetic. We covered which group? Pitot-static. what three instruments are the pitot-static instruments? Say that again, Anders. Airspeed indicator. We say that one first because of the fact it is connected directly to what? The pitot tube. Okay? So that's the airspeed indicator. Okay, next, Joseph. Vertical speed indicator, which what gives us what kind of information?
Your speed going like up and down, like 3,000 feet per minute.
The rate. So it's a ratio. Something per something else. So it's a rate. So it gives you your rate of ascent or descent, right? Vertical speed. Okay. What's the third one, Elijah? Okay. Altimeter. What does that do for us? Okay. What altitude on what type of scale? Solomon?
Never mind.
Elijah? Feet. Okay. Feet. But we know there are 4 different types of altitudes. What is it?
Indicated altitude, true altitude, pressure altitude, and density altitude.
Okay. Which one of those are we talking about? Which one of those is mean sea level? Which one of those is MSL, Mike Sierra Lima, mean sea level? We have MSL. We have AGL. What is AGL? Sounds like we need to do AGL, above ground level. So out here in our part of the world, we may show that we have an altitude, an indicated altitude, MSL of 9,000 feet, yet we're only 1,000 feet above the terrain, if that. So those are the different types of altitudes. Review those. Okay. Oh, did you not come to school today? You may borrow a pencil.
I lost a pen today.
Doggone it. So, understand what the different altitudes are. We talked about our airspeed indicator. What kind of speeds do we work with as pilots? Solomon.
Indicated.
Okay, indicated. Where do we see the indicated airspeed? How about on our airspeed indicator? Okay, there we go.
I was like talking about. I thought you were talking like where is it on the PFD? That's what I thought. That's what I thought.
Yeah.
Well, it's definitely on the right side of the plane indicator on the horizon.
It'll actually be on the left,
Yes, should be way on the left.
because the thing on the tape on the right is altitude, right?
Yeah, I was reading way too quickly.
Okay. So we have indicated airspeed. What are the other types of airspeeds that we have? Solomon?
True airspeed.
True airspeed, okay.
Calibrated airspeed.
Calibrated.
And vertical airspeed. Wait, no.
What's a ratio?
Ground speed.
Ground speed. Those are the 4 types of airspeeds. Review those. Know what they are. All right?
Is there also equivalent airspeed?
Not that we deal with.
Oh, okay. So I'll just scratch that out.
Well, you know, it's just not something that we deal with. Okay? So, airspeed indicator, altimeter, vertical speed. So when we look at those, and we look at these on kind of the old analog gauges here. Oh, hang on, there's that. Why isn't that working? Give me just a second here. Hang on here. I don't know why that's being finicky today again. Okay, there we go. So when we look at the analog gauges, what gauges from left to right are we looking at here? Okay, when we look at the analog, which ones are analog? These, correct. From left to right, we have what? Altimeter, vertical speed, and then airspeed. Again, the airspeed indicator is connected to something different than the other two. It is the pitot tube. Okay, so that's what that looks like there. Then, when we look at a primary flight display, like we see over here, where's our altimeter? Solomon?
On the right.
So the altimeter tape is here, correct?
Yes.
Yes. Vertical speed is where?
Right next to it.
Here to the right. So this is our vertical speed indicator. What do these numbers mean?
1,000 feet, 2,000 feet.
Okay. So the hashes, the small hashes, are in 500 feet increments. So 500 feet per minute, 1,000 feet per minute, 1,500, 2,000, etc. So this above the line is going to be a climb. This below the artificial horizon line is going to be a descent. Correct? So here in our altimeter, then these are basically broken down in increments here of, in essence, the big hashes are hundreds, but then you have 20s. So 120, 140, 160, 180, 200. So the small little ones are in 20-foot increments. And then, as we said, our airspeed indicator is where? On this left side. This, by the way, is a brand new program that I got from Cessna. And I just got it loaded. They just sent the little disk thingy here for me to load. As soon as I get the rest of it installed, we'll be able to kind of use this sort of like a real time, where I can basically program this to say, here's what it looks like at X number of feet at this altitude going wherever it is that we're going. So you guys can see what that looks like sort of like in real-time flying. It does have synthetic vision, and this one actually, the version that I have here is a turbo stationaire with the what they call the Cessna Nav 3 package, which is the electronic version of everything. So our thanks to the folks at Cessna for doing this in particular. Zach Powell, thank you, buddy. Appreciate that very much. So as we look here, we see that the three pitot-static instruments represented here vertically by tapes, right? Now you'll notice here the numbers. So we have 30, 40, 50. This represents what? Knots. Nautical miles per hour, indicated airspeed. Okay? Why do you think this red exists here?
It's your stall speed.
So you're telling me that this entire range is a stall speed? Could be. It could be. But that's definitely an area where you notice that you're in this part of the airspeed tape. You better be doing it on purpose. Okay? The white, that kind of gets into that range here. The bottom of the white arc gives us the stall speed here of the full flaps. So on this particular airplane, full flap stall speed, you can see right here it shows us about 47 knots. So you'll see red, white, green, yellow, and then a red line at the top, just like you see on the analog instruments that you see with the airspeed indicator. The difference is that when we talk about the bottom of the white arc on the digital display, there really is kind of a bottom. In other words, you know, it's because it's a vertical presentation, there really is kind of a bottom, whereas the bottom of the white arc technically is at the top part of the airspeed indicator, and sometimes that gets confusing. So just know that the low number is what we call the bottom. Make sense? Okay? So as we look at this, and we look here, something is, oh, that's what's catching. As we look here at our primary flight display, what we're looking at from a digital standpoint, the background of the primary flight display on a G1000 display is which instrument? Solomon.
On the horizon, wait. What was the question again? I was way too fast.
The background, the background that you see on a G1000, in this case with the one that you're seeing now, the one that's in your book, is just a standard horizon where you have blue on top and kind of brown on the bottom. Blue's the sky, brown is New Mexico. And when we look here at the one with the synthetic vision, then you'll see the bottom of that, it'll be green, representing, you know, the ground, depending upon what part of the world you're flying in. That green color, that's a part that changes with your altitude. So there's a legend that actually tells you, kind of to say, here's how you can sort of tell where you are by the color of that lower portion of this particular instrument. And it is basically, it encompasses the entire width of the screen. What instrument am I talking about?
The GPS?
What instrument? Attitude indicator. So now we're talking about what type of instruments. 3 categories. We've talked about pedostatic. Yes.
Okay, I have a question about the
Let's answer this question first.
my question.
No, the question I asked. Gyroscopic. So the attitude indicator is the first of what we call the gyroscopic instruments. Joseph, you had a question.
Okay, so it's about at the lower bottom right corner
Mhm.
of the G1000.
Uh-huh.
The LCL.
Uh-huh.
I think it's called. Is that clock?
Yes.
But why is it 18 for me?
It's showing local time. And again, this hasn't been set up. I just got this loaded. Oh, yeah. It just got loaded. So, but that is a clock. Okay? So now we start looking at the gyroscopic instruments. Which instruments are gyroscopic instruments? Hang on here, guys. Something has just, there it is. Test 1, 2, test 1, 2. I lost the microphone there for just a second. Okay. Which instruments are our gyroscopic instruments, Anders? Attitude indicator? Solomon?
Attitude indicator, skids and slip skid indicator, and horizontal situation indicator.
Okay.
Is there a fourth?
No. No. We call them something else. But that's, you're on the right track. The attitude indicator, heading indicator, turn coordinator. Attitude indicator, heading indicator, turn coordinator. Just a little bit of information on kind of the differences with what Solomon was just talking about there. The turn slip indicator is an old-fashioned way of saying turn coordinator. So it's not incorrect. It's just what we used to call it. And in some cases, they can be different with analog instrumentation, but it is, with the G1000, it is a turn coordinator. Then the heading indicator, it can be an HSI, or horizontal situation indicator, if it has something else with it. So what would a heading indicator have to have in addition to just pointing out your heading for it to become a horizontal situation indicator, like you see over here on our G1000? What would it have to have? First of all, where is it? Is this it?
Yeah.
Okay. So here we see the heading indicator. The heading indicator, we have 360 degrees that we can choose from to fly a particular heading. All right. We also have some other stuff kind of going on this. For instance, what's happening here?
Your course is telling you where you need to be heading, and the little line in the middle moves if you're off course, and you
Okay.
gotta, follow it and get back on.
Good. So this gives us information with regard to navigation, right? So it can be a GPS, like you see here with this magenta line. It can be a VOR, and we'll talk about what a VOR is later, but that's a radio-based navigation unit. Well, parts of a VOR can be a waypoint, but a VOR is a little different. And then you have two different types of VORs. So for your heading indicator to be a horizontal situation indicator, or HSI, it must also include navigation information. Otherwise, you can have a heading indicator that just gives you your heading. But for it to offer navigation assistance, you would then call it an HSI. This is certainly an HSI. All right? So, attitude indicator, heading indicator, turn coordinator. So those are the three. Now, as we talk about gyroscopic instruments, and I'm not sure why I keep losing the microphone. I don't know what's going on here. Guys, let me check this out. I don't know what's happening. Oh, there it is. Check 1 2, check 1 2, test test test. I don't know if I'm not I don't know. So tell me how gyroscopic instruments work. How does a gyroscopic instrument work? The assumption is here is that you all have read chapter 8. Elijah.
So like when the gyroscope is spinning,
What's a gyroscope?
it's like a wheel.
Okay.
It spins, it stays in a constant.
What kind of a wheel is it? Kind of like a flywheel. What would we call that? Are you familiar with the term inertia? Okay. All right. So we have this weighted disc that at some point needs to do what? Has to spin. By its spinning, we'll talk about how the spinning happens here in a minute. By its spinning, and this disc happens, tell me where the magic happens there with gyroscopic instruments. Okay. Okay, so now you're saying that you get certain indications from it as there is movement around the gyroscope, correct? How can that happen? How does that work? Solomon? What do we call that? What do we call that part where it tries to stay in place? What do we call that? No. What do we call it? What do we call it? Rigidity in space. This is the principle by which a gyroscope gives the pilot useful information. The inertia wheel on the gyroscope, once it starts spinning, and it has some mass to it, when it gets spooled up to the right speed, it becomes somewhat stationary. It sits in a cradle in this mechanism called a gimbal. A gimbal allows stuff to happen around it. So it allows movement around this in this gimbal mechanism. There are, in the old instruments, mechanical linkages to this type of movement there that is sensed inside this case. So each instrument, each attitude indicator, heading indicator, turn coordinator has a spinning disc. Each one inside that case has this mechanism. The plane senses the movement around those spinning discs, around the gyroscope. So that's what it's sensing. In essence, you're turning or climbing or descending around the instrument. And the indication that you get on the face of the instrument indicates what that change happens to be. The disc wants to stay in one spot. Anytime it senses something trying to move it, that's where you get a change in the indication on the face of that instrument. Now, what keeps that disc spinning? A vacuum pump. How does that work? Okay. What is it around the gyroscope that allows that air to actually have an effect? Little indentations in it. How many of you guys have seen pictures of what we used to call an old grist mill on a river? Got a big wheel, and on that thing it's got buckets. And as the water hits those buckets and it moves that, it does what? Turns a wheel. These operate on the same principle. But the fluid medium is not water, it's air. And that air, there's a little teeny tiny little nozzle that blows across the edge of that gyroscope that hits those little buckets that spins that wheel. They also do them now electronically, where that wheel is spooled up electronically. So we don't have vacuum pumps anymore the way that we used to. Vacuum pumps were prone to fail. So let's think about this. Let's say you lose a vacuum pump. What can fail instrument-wise on your airplane?
You could
What
tell if you were skidding.
what instruments?
The attitude indicator, heading indicator, and the turn coordinator.
Correct. You could lose all three gyroscopic instruments. Imagine being in the clouds and not being able to tell which way is up. That could be bad. Right? Elijah.
Why did they decide when making gyroscope, when making the thing to use a vacuum pump over like an air compressor?
Well, an air compressor. I suppose you could miniaturize some form of an air compressor. The pump itself kind of does that. But again, you have to think of something that's got to be lightweight. It's got to be small. But those things were prone to failure. And I've had them fail on some of the old airplanes that I've flown. So when we get to the interpretation of instruments, you'll find that even though you're going to hear me say that the attitude indicator of all the instruments is the alpha and the omega. Your attitude indicator is the alpha and the omega. What do I mean by that? If I tell you that your attitude indicator, which on the electronic displays like we have in our training aircraft, if I tell you that that attitude indicator is the alpha and the omega, what do I mean? Check 1 2. Test 1 2. Test 1 2. Test 1 2. Check 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 check. Check 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 check. Check the volume now, Joseph, and just see. We should have volume now.
Alright, might take a second. Ooh, live chat.
Yeah, let's not do that. Check 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 check. Test 1 2. Test 1 2. Test 1 2. I don't know what just happened, but okay. So getting back to this, guys. What do I mean by the attitude indicator, which is, again, the back... Turn that off. The background of the G1000. What do I mean by it being the alpha and the omega, Elijah? Say that again. When I say alpha and omega, what do I mean by that? Alpha is the beginning. Omega is the end. The attitude indicator, it's the beginning and it's the end of your instrument scan. Your instrument scan means that you cannot just rely on one instrument. You have to look at all of your instruments to interpret the condition of your craft and your place in space. But when you do, no, you go in a wagon wheel. So when you do, you begin and end with the attitude indicator. So you begin by looking at your attitude indicator, then your airspeed indicator, then your attitude indicator, then your altimeter, then your attitude indicator, then your heading indicator, then your attitude indicator, your vertical speed, attitude, coordination, attitude, and you begin that again. So you start and you begin and end, and it's a continuum, so there's no real end. But it's a wagon wheel where you look at the attitude indicator, then airspeed, attitude, altimeter, attitude, heading, attitude, vertical speed, attitude, coordination, attitude, airspeed, and it just continues. This is how you do it. Okay? When we looked at physiology, one of the things that I told you was that when you looked at the inner ear, and we looked at the tubes inside your ear, you have a tube that is set vertically, one is set at a 45-degree angle, and you have another one that's set horizontally. The same is true with the orientation of the gyroscopes in your attitude indicator, heading indicator, and your turn coordinator. All three of those instruments have a different type of a profile with how that is mounted to give you all of that information. And to me, it's always been so interesting is the fact that we use kind of in essence the same type of movement orientation for us as humans as we use in the airplane to understand, are we standing up? Am I leaning forward? Am I leaning back? Am I listing off here to the right? It's the same type of thing that we use in the airplane for you to understand which way is up. Am I leaning? Am I slipping? Am I skidding? Am I climbing? Am I descending? Are my wings level? Am I turning? And that's what we use. So those are the three gyroscopic instruments. How do we know that those instruments are working properly? Would you fly an airplane that you had no idea if the instruments were responding appropriately? Okay? So you would think then that we do have a way to know if they're working properly. How do we know if they're working properly?
Test.
What kind of test?
I'm sorry.
Like a button that you can like press. And
Say that again. What happens when you can't look outside? Let me ask you this. Would you even take off if you didn't know that they weren't working properly?
If we're talking about digital, then you can test it.
I'm talking about these. I'm talking about steam gauge. I'm talking about this stuff. And the electronic ones are the same as well. So how do I know that these are working properly before I take off? Bang on them? Maybe not.
They all read 0.
If you're at Aspen and you're like, I mean, technically, when you're sitting still, they shouldn't be moving, right? But then at some point, you have to get from the place where you started your engine to where you can take off, right? What do we call that? Taxi. So let's say this. Are you always just going to be in a straight line to the airport, to the runway? You're going to make some turns, aren't you? So what do you check to make sure that your instruments are working correctly?
You can try taxiing a little to make sure.
Say that again. Your heading indicator. What's going to happen with your heading indicator when you make a turn?
It'll turn a 45-degree angle.
If you're turning 45 degrees, then it will, I guess. I mean,
You're going to make a series of 90-degree turns, right? So we can check that. So your heading indicator, you can check that on the ground before you launch. What about your turn coordinator?
No, not until you're in the air.
Really?
Or if you like, if you Tokyo drift or something.
no, please stop. Please stop. Thank you.
The turn indicator.
So when you turn an airplane on the ground, are you able to get a bank?
No.
No. So what's going to move? What's going to move on your turn indicator?
Oh, the little bead.
The little ball. Okay? This little inclinometer. Okay? So your inclinometer is going to go toward the outside, right? So we can check that when we taxi. What else?
Well, if you go to the run-up area, you can check your engine, fuel pumps,
What are we talking about right now?
the three major.
We're just talking about gyroscopic instruments.
That are involved with the gyroscope.
Okay? My point is that we check these things on the ground before we launch to make sure that they work. So your turn coordinator, your heading indicator, we want to see that turn in a commensurate fashion to the turns that we're making. And we also want to make sure that if we're taxiing to the south, that we get what kind of an indication on your heading indicator? That you're going south. So you want to make sure that works, right? So what about your attitude indicator? What's going to happen there?
If you go up a bump, like if you go up a bump, you can test and see if it goes up and down.
Possibly.
Well, speed bumps.
Yeah, like put some speed bumps on
You're
it.
going too fast.
Speed bumps all the way down the runway.
Yeah. Don't go too fast. Children at play.
I wasn't really talking much about a speed bump. I was just talking about like a general bump that you could put on a taxiing road, not on the runway, because then they're going to be going in
Any
over
well
100
care.
knots or less. But like if they're like taxiing, and they like go to park. I don't know what the plain term is for parking. Is it just park? Okay, well,
Mhm.
if they're parking somewhere,
By
there could be bumps.
Shh,
There could
shh,
be
shh,
bumps.
shh, shh, shh.
So then, if they go up and down, their gyroscopic device would read that, and it would show up on the attitude indicator, and it would possibly mean that it's working a-okay.
On the old analog style of attitude indicators, you do have a way of repositioning the little miniature airplane horizontal with the artificial horizon on the attitude indicator. Well, you just kind of push it, and it kind of recages it. And then you can move it up and down if you want. So yes, it's like a little knob or a button. Depends on the type of indicator that you have. What happens when you begin to taxi with your airplane? Is it going to stay flat? That nose may want to come up a little bit as you start, right? So in that, you may see a little bit here where your attitude indicator shows that perhaps you have a little bit of an increased angle of attack. What happens when you brake? Might do this a little bit. So you should be able to see that moving vertically. Also, on the synthetic vision components of like what we have here, what's another way of telling as we taxi and we make these turns, we can see what moving in here in our screen for the synthetic vision. Look at the picture. So now this, you're over what eastern Kansas. So on that, on the digital display, the G1000, it looks pretty flat. What would it look like here in the mountains? A lot of mountains. Shows that over there on the primary flight display on the picture that I took there of the Diamond DA40. So you'll see those mountains kind of move around there as well, right? So that's another way to tell, is this working correctly? Traffic. You may be able to see traffic moving around on this screen here as well. So there's a lot of ways for us to check our instrumentation before we launch. The G1000 is almost cheating because it runs a self-diagnostic as it spools up, and it will tell you if it's working properly or not. But don't get into the habit or into that pitfall element of relying on that. Engage the supercomputer here and see, does this make sense to me? Practice that on the ground before you get in the air. Make sense? Okay. So when we look here at the turn coordinator, we've got a couple of things going on here on the turn coordinator, right? We show with the airplane indicates that we are what? Banking. Thank you. Banking. Not necessarily turning. Even though this is a turn coordinator, what that shows is the bank angle. What do these little hash marks mean? Solomon?
Wait, which hash mark? Those hash marks?
Joseph?
They're the skid marks. Like how on a G1000, it's the thing at the top, like your degrees. That's level.
Okay, so those two hash marks, if you have your wings on those two hash marks, what does that indicate? Your wings are level. Okay? So we have those. What does it indicate? Broadcast, and by all appearances we should be live. Live there, and back here. Okay, so hopefully at home people are actually being able to hear what we're doing. We had a little audio issue in the middle school class, and I really don't know what happened. But we're going to pick up here with weather, with wind shear on this as advertised. What is wind shear? What is that, gentlemen?
It's the variation of wind and or direction from place to place or from one altitude to another.
Excellent. Excellent. When can it happen? Anytime. Are there times that it is more reasonable to expect wind shear conditions than perhaps others?
In the mountains,
Anywhere. Are there times that you can expect it more perhaps than other times?
specific fronts, or
Okay.
takeoff and landing, maybe?
Okay. Has to do with weather. So, in the morning, is the air typically more stable or less stable?
More stable.
Why?
I do not know.
Has to do with temperature. Temperature is a little bit more even, and it's not until the sun comes out and does what that changes. Heats the ground. When it heats the ground, now the temperature warms up. What happens to the air? It starts to rise. Convection, right? So when that happens, now you start getting periods now where when you're flying and you hit this air that's rising, it can get a little lumpy. Okay? As it gets a little lumpy, the atmosphere becomes a little less stable, then the chances of wind shear starts to go up. Around a high pressure system, chances are things are going to be pretty stable anyway. But if you're flying in and around a low pressure system, you might expect a little more turbulence and therefore a little bit more wind shear. Flying through a temperature inversion, you should always expect wind shear. Flying through or flying over or crossing a line of a strong front, you know that you're going to get a temperature change and a change in the wind direction, so you should expect it then. And anytime there is thunderstorm activity, you should always expect that to happen there. Also, anytime the winds are greater than 25 knots over the ridges, you should also expect wind shear in certain isolated locations, because that stuff can just come out of anywhere. All right? So, these are some of the areas here that we can see. And again, as Cooper deftly read there for us, that's where they can happen. The big thing, guys, is understanding it can happen anywhere, anytime. Wind shear on approach. Let me ask you a question. Those of you that have gone through the training on the desktop sims, why is it that I am such a zealot about keeping your hand on the throttle anytime you are at or below 500 feet AGL? Because when those conditions change quickly, what is going to be an asset that you have? Power. Use it. That is why that when you start the Flight Academy piece, you're going to hear your instructor talk to you about you only remove your hand off that throttle when you're on the ground or lower than 500 feet AGL when you have a compelling reason to do it. Let's say, for instance, you're flying and you're just taking off and you're asked to change frequencies or whatever. You could do that. Normally you're going to fly with your left hand and you're going to change that with your right, but then your hand comes right back down onto that throttle. You just never know. So that's one of the reasons why. Expecting that wind shear on approach. When you have windy conditions or you're flying through a temperature inversion on your approach, you can expect that to happen. Your airspeed indicator is going to be a pretty good barometer of what you might expect, as well as knowing what the temperatures are at the various levels as you're beginning your approach. When we get to the instrument side of this, you'll see what I'm talking about with kind of how this whole thing works, because you may start your approach with a headwind, but then all of a sudden you're faced with a tailwind. And so you've got to be able to then adjust that power quickly and efficiently as you need to. Wind shear terminology. Updrafts, downdrafts, pretty self-explanatory. Low-level wind shear. What are we talking about there? What is low-level wind shear? Anytime we're near the ground, typically 3,000 feet AGL or lower, that's low-level wind shear. You may hear that reported on the ATIS when you're landing somewhere. You may hear that. Now, does that mean you can't land? It just means you got to be cautious. You've got to be ready. Remember this. The only time that a go-around is the wrong decision is if you're out of gas or on fire. Okay? A go-around is never the wrong decision unless you're out of gas or on fire. Okay? So that always keep that in your quiver of things to do. Okay? Effects of wind shear on an aircraft. What do we think those things can be? One of the big things that we'll notice on wind shear is we're going to notice a change in our indicated airspeed. You may notice the ground speed, but that airspeed indicator is going to be kind of a big deal that you have right there. So as you look at this, what is the wind shear component that we're looking at here? If you look at figure 30-6, what are we looking at? We're looking at a very real approach. Now, again, the angle that they're coming in here, they're coming in at a 45-degree angle. That's not the way that we normally do that, you know. But understand that the airspeed up higher is almost always going to be a higher airspeed than the winds down low. So are you constantly going to be changing then your power settings on your way in? Yes. Again, another reason why you keep your hand on that throttle. What indication do you have in your airplane that your airplane may be getting close to stall speed? What is the primary thing that you look at?
Your controls will be getting floppy. The stall will.
Your airspeed indicator. You're constantly watching your airspeed indicator. When you guys fly with me and you go watch some of the videos that we've done, you will always hear me on final calling out my airspeeds. You'll always hear me calling out those airspeeds. Why do I do that? Forces me to look so that I know, am I getting too slow? If I'm getting too slow and I'm high, what can I do? I can lower the nose. But if I'm getting too slow and I'm low, what do I do? Okay? So you're pitching for an airspeed, powering for an altitude is kind of the way that works. Except on an instrument approach. More on that later. So these are the conditions that you can expect. You can expect changing wind conditions even if the wind is coming right down the runway. Right? That's what figure 30-6 shows us. It's that sudden drop in that forward airspeed that your airplane is configured for a particular descent at a particular airspeed. Then all of a sudden you lose that headwind and you get that tailwind and you get this. That's why you constantly have to have your hand on that throttle, because picking up an unforecast tailwind over the numbers, just like when you're landing and you're beginning your flare, is not uncommon. And so you have to be ready, because you do not want to let that airplane drop. Effects on the flight path, we talk about overshoot and undershoot. So as we look here at the overshoot and undershoot, let's look at this. Remember, in this figure that we're looking at here, figure 30-7, understand that the angles that they're showing you here are, for dramatic purposes. You would never normally, have that kind of angle of attack. Do these make sense to you guys? Do you understand kind of how this might work? Okay? Because again, remember, it's like if you look in the lower left and you see that you've got a higher wind and then a lower wind, ultimately it's going to push you, but you're going to drop. And so you constantly want to be checking out that airspeed indicator to know exactly what's happening to your craft. You will also, in some cases, be able to hear a difference of the wind going around your canopy, even with your headsets on, to hear that difference flowing around that canopy. So that can be another big indicator here. The downdraft here, you can be all set up, and then the next thing you know, you're way, way low. Or you get that big updraft, the next thing you know, you're too high. Yes, dear.
So if you found yourself in one of these situations, would you just adjust power accordingly?
Correct.
Okay.
Correct. Now, let's take a look at this. 30-8. If we look at figure 30-8, one of the things that we see here is that this is an actual, that stereotypical wind shear where you have winds coming out of opposite directions at a very thin altitude band. So you're coming down and you've gotten the ATIS, your weather report, that the winds are coming one particular direction. You choose your runway based on those winds on the ground. But you'll notice that you have a tailwind coming into that, coming in on final. Well, when that happens, one of the things is that you're praying, first of all, that the forecast is, or that the report is correct still. Second of all, you may want to contact Tower and ask for instantaneous winds. Tell me what the winds are right now. Now, why would you ask for instantaneous wind as opposed to just a wind report? Possibly.
Would they give you like the old report, but if you said instantaneous report, they would give you what it said?
You're on the right track. Normally what they give you is a 10-minute average. That's normally what they give you unless you ask for an instantaneous wind report. If you're so far out that you cannot make good visual contact with the windsock, or if you're in instrument meteorologic conditions, you can't see the windsock, ask for instantaneous winds. What are the winds now? Because in that way they'll still tell you if they're in the direction that you need those winds to be, so that you have some form of a headwind in order for you to land. Because that'll pucker you up pretty good. If you notice that you're on a 3-mile final and you're thinking, holy crap, you know, I've got a 40-knot tailwind. What are the winds on the ground? Well, if the winds on the ground are a 5-knot headwind, guess what's about to happen? Somewhere between here and here, you're going to get that wind shear, and you're going to fly through that zone, and you better be ready. Okay? Notice this here as well. What do we know about the winds? The higher winds are going to be stronger, the higher above the ground they are, right? The closer you get to the ground, in most cases, the slower the winds. So here you are set up just like you see here in figure 30-9. At 1,000 feet, let's say, you may have a 20-knot crosswind component. But by the time you get to 50 feet off the ground, you may have like a 5-knot crosswind component. So are you constantly making adjustments here? Now in this case, it may not necessarily be a power adjustment. This may be a rudder adjustment. This may be an actual control adjustment here. But you're constantly making those adjustments, either visually, as you visually see the runway, or on an instrument, checking out your course deviation indicator on whatever you're using, whether it be a radio navigation or a GPS-based kind of a navigation aid that you're using on the way down. So, power is one, but your actual directional component is going to be another way to counteract the effect of these changes in wind velocities. Causes of wind shear. When you look at these bullet points, know each of those bullet points. They are test questions. Okay. In the margins, right here, Harris, what does it say right there in the margins on that last paragraph on page 665?
Avoid thunderstorms and cumulonimbus clouds.
See, right there it says that. It says avoid those things. Why do we want to avoid thunderstorms? Because they're bad juju. Okay? They will be that thing that will rip your little aeroplane apart. Cumulus clouds, cumulonimbus clouds. We haven't gotten into the nomenclature yet of clouds, but cumulonimbus clouds are like big rain producers and ultimately can become thunderstorms. Why do we want to avoid those? Why do they exist? Why does a big rain cloud exist? First of all, it's got a vertical component of lift. You have instability in the atmosphere, and you've got enough water vapor to make it all happen. Those are the ingredients to a thunderstorm. So you've got that vertical lift in an unstable atmosphere with plenty of water. You do not want to tangle with those. How far away from thunderstorms does the book tell us to stay? 20 nautical miles from the footprint of the thunderstorm. 20 nautical miles away from the footprint of the thunderstorm. The reason I emphasize the footprint is because sometimes these clouds are not just cylindrical. You can look over at and you can see a cloud and you can say, okay, from here to there I'm 20 nautical miles away. But if you look up, you may only be 10 nautical miles away because you can get that big anvil, that big mushroom look around it. So you want to stay 20 nautical miles away from the entire footprint. If you look at a plan view of that thing, you want to be far, far away from that sucker. Especially out here on the windward side of it, where it can ultimately, you see that big anvil cloud of a lot of these thunderstorms like that? It'll spit hail out the top of that in like this big plume. I've actually seen that in the air. And it's like, you've got to be kidding me. But people try to fly through it, which is bad. What's a pi rep? It says pi rep is strongly encouraged. What is a pi rep? What is that? It says right there, pi rep. Pilot report. Why are pi reps useful?
Because is it a report from another pilot?
Yep.
I think it could be useful because they already flew through the conditions.
Here's what I just saw.
Like,
Here's what's happening to me right now.
like I just landed 5 minutes ago. Be aware of this.
I know what's forecast. I'm up here right now. I'm at 10,000 feet. I'm over this particular landmark. Here's what's happening to my aircraft right now. That's pretty useful, right? Pi reps, when you're flying, are some of the most valuable pieces of information that you can get as a pilot. Everything else is going to be a forecast. Everything else is going to be a guess. Give me an observation. I'll take that every time. Okay? Let's take a look here. Oh my goodness. What could possibly happen here flying underneath the base of a cumulonimbus cloud on approach? What could possibly go wrong? Yup. And the catastrophic ending of that could be what? Yep. Undershooting the runway, hitting the ground short of the runway. Because there's some of this stuff, ladies and gentlemen, you cannot fly out of. And as evidence of that, write this down. You can Google it. Dallas, summer 1985. An L-1011 on approach into Dallas in 1985. I want one of you to tell me about that tomorrow morning. Okay? I want to say it was a Delta flight. I could be wrong. Okay? I happened to be in Dallas at that time. I was about 20 miles away from the airport.
In the sky. What has been the worst weather that you've ever flown in? Like, I know you've probably
Personally flown in, severe turbulence. That's the worst. Just clear air, severe turbulence. We slowed down past VA, and it was the only time that I really kind of wondered if I was going to be able to land the airplane. My head hit the canopy so hard, and I thought I had my seatbelts on pretty tight, pretty snug. Come to find out, you can snug those things up a lot more than you think. But it dazed me. So let's take a look at this. Let's examine what we have here. So here's your desired approach path. And again, in this case, guys, understand that these are exaggerated approaches because your approach actually is going to be like over here around 3 degrees. So here's your desired approach path. Notice that you're flying into a headwind as you approach the downdraft of this cumulonimbus cloud. Now you have this increased performance due to the increased airspeed caused by the increased headwind. Then all of a sudden, now you get shoved down and you start to notice that here you are, I am losing altitude. My airspeed is the same, my configuration is the same, but I'm losing airspeed like I don't know what. It's like I'm falling out of the sky. What is your first impulse? Power. Power, power, power. So, and this was the thing that you're going to see here is that the crew didn't recognize quickly enough what was happening to them. The downdraft pushes them down. Now all of a sudden you got a tailwind. What happens to your airspeed now? Goes in the tank. Your airspeed goes in the tank. Your ground speed may increase, but ground speed's not going to keep your airplane in the air. What keeps your airplane in the air? Indicated airspeed. That's what you've got to have. Okay? So, is it 12:30? I'm going to go till what, 12:40? What time are you guys leaving? Class starts at 12:40. Okay, I'm going to end it here, guys, on air masses and frontal weather. That is where we will begin tomorrow morning. Air masses and frontal weather, and I'm going to pick one of you 5 to tell me what happened in Dallas in the summer of 1985. Okay? All right. Guys, thank you very much. And thanks for coming to Taco Tuesday.